Welcome to XMaths. My name's Lee. Today we'll be looking at our second part of linear programming. Last time we had a look at inequalities and we slowly worked it into linear programming, but now we're actually going to do the linear programming. I'd like to start by starting with the question we ended off with last time. So let's just go to that and see what it says. As you remember, we were looking at this graph, and what it had asked us to do was to work out the equations of this feasible region. And we had done that all, and we hadn't actually put it together as a list yet, so let's just do that so that they can see it. Basically, we'd had x greater than equal to 15, y less than equal to 20, y greater than equal to 5, and we had x smaller than equal to 40, and then we had y greater than equal to minus x plus 30, and y smaller than equal to minus a half x plus 30. Okay, so now that was great. And now it starts talking about the objective function, and that's what we never got to last time. Now, as I explained to you when we were going through the terminology, the objective function is the thing we maximize or minimize. Now, in this case, they want me to use this equation to determine the maximum value of p. Now, to do that, we have a choice of three methods. And I'm going to show you all three using this example. And then we will choose one and we will stick to it. But I just think it's important you see all three because sometimes the one method is more useful than the other. The first method is the method of your corner points, or if you like, simplex method. Now, what that involves is you would take this feasible region and you would calculate or read off the coordinates of each of these points. So over here, let's call this A. If I looked at A, it would be 15, and that is, let's just make sure, that's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it's 15, 15. So A is 15, 15. Your B, that's going to be easy to read off. It's going to be 15, 20. Your C, at least you know your Y value is definitely 20. Let's figure out your X value. That's 15, 16, 17, 18, 19, 20. That's 20. Let's look at our D, which I'm going to put down here. The X value is 40. And that's 6, 7, 8, 9, 10. Now you can see I'm just reading it literally off the graph, which is absolutely fine if we have accurately drawn it using graph paper. Now, E is the coordinate 45, and F over here, that's a 5 over there, and this is going to be 20, 21, 22, 23, 24, 25 over there. Right, so we got the corner points. Now, you can see that that's a little bit of a hassle in the sense that you have to sit and read them off, but it's actually quite a safe, secure way of doing this. Because what we're going to do is we're going to say to ourselves, let's see if we substitute these corner points into our P equation, which one gives us the most. So let's take our P equation, which is 10x plus 4y. Now, we want to know what happens at A. Well, it will be 10 times 15 plus 4 times 15, which will equal 150 plus 60, which is 210. Right, let's see the P at B. B, we're going to say it's 10 times 15 plus 4 times 20, which is going to be 150 plus 80, which is 230. All right, the P at C. Our C value is 2020, so it's 1020 plus 4 times 20, which is going to be 200 plus 80, which is 280. Then the P at D is going to be 10 times 40 plus 4 times 10, which is going to be 400 plus 40, which is 440. Now you can see that's much better than these options so far. Right, the P at E is going to be 10 times 40 plus 4 times 5, which is going to be 400 plus 20, which is 420. And then the P at F is going to be 10 times 25 plus 4 times 5, which is 250 plus 20, which is 270. Now you can see that if we want the maximum value is at this point, so D is where we get our best solution, our maximum solution for P. So going back to our graph, we are saying that this is our maximum solution. Okay, so that's what we call the corner point or simplex method. Now, the disadvantage of it is if you've got lots of corner points, as in this one where you've got 6 of them, you have to take all 6 of these points and substitute them in, which can be very time consuming. Secondly, the second disadvantage of it is the fact that if you are using it and you have to find these corner points, they might not be so nice and easy like these were to read off. You might have to find a whole lot of simultaneous equations. So if you had 6 points to calculate, you'd be doing simultaneous equations till you were green in your face. So generally, it's not the easiest way to go in terms of time. It is an easy method, but time-wise, it can penalize you quite heavily. So what's your second method? And the second method is called the search line. Now, this one is actually taught in your matric year. Some teachers teach it in the grade 11 year, and I must admit I'm guilty of that, because I just think to myself, let's teach you all at once, then you can actually have an informative choice about what's best to use. So let's have a look what this is. It says 10x plus 4y. Now, the search line method works as follows. What we do is we go to this equation we want to optimize, and we get y as the subject of this equation. So over here, I would probably spin it around. So I go 10x plus 4y equals p. And then I would say, well, that means that 4y is minus 10x plus p. And now we divide through by 4. So y is equal to minus 5 over 2x plus p over 4. Now, all I've done is change the way that equation is written. But why I'm doing it is I want to actually work with the gradient. The gradient of that line is going to give me the search line. So I'm going to use the gradient of minus 5 over 2. To do that, I'm going to go up to my graph that I drew. Well, I didn't draw in this case, they had drawn for me. And I know that the gradient I want is minus 5 over 2. Now, what I do is I go over here and I'm going to work out the gradient on these axes. Now, of course, I can use 5, literally starting there, and 2 there, which is fine. So I could go here and here. And say, okay, let's put up our search line. Let's get hold of that. Let's use this one and put it in there. Now notice I'm using the dotted line to be my search line, so I don't get confused between what is my search line and what are my actual equations for this particular situation. Okay, so there we are, ready to go. Now, you can see the gradient's 5 over 2, but I could have just as well used 25 over 10. And have got another line over there. So if I did that, 21, 22, 23, 24, 25, there we are. And 10 is over here. And if we drew in the line over here, let's use this one again. Hopefully you will see that that line is parallel to this one, if it's been accurately drawn. And you can search with this one or with this one. Okay, so it's up to you. Let's stick to the one I did initially, but you can see you can use any proportion to get a nice easy line. We will be doing a lot of that, so again, don't worry, we will be meeting up with that again. Right, so now what we're going to do is we're going to take this thing which I've just put in, and we're going to search the feasible region to find the last point of contact if it's maximizing. If it was minimizing, it would be your first point of contact. So literally, you're going to pick up this line and you're going to move it. Now, of course, With you, I've got a nice technology here, which makes it really easy. With you, you're going to be using your ruler to do this. You're going to dot in a line that represents that. And then you're going to slide your ruler in place of that line upwards through the drawing to its optimal position. I'm lucky, as I say, I've got the technology, so I can just move it. And so let's do that right now. Let's pick it up. And what I'm going to do is I'm going to slide it. Very important, I keep it parallel. Now, the good thing with my technology is it does keep it parallel. Now, if I was minimizing, that would be my solution at A. But I'm not. I'm maximizing, so I carry on sliding through the feasible region. And you can see E, it's still got to go through D, and you can see at D is its last point of contact. Now, that is what I found when I was working with it earlier on, the other method. So D is where I would actually get my optimal position. And just so that we've got it in place, I'm going to actually put that search line back where we had it and just label on it search line. And I would suggest you do that as well. It helps your examiner to see what you're doing. They know this is the line you're searching with. The optimal position is not essential. That's really up to you. You can decide to put it there or not. Okay, so now if they say indicate the optimal position, then you have to do it. But if they don't say anything, it's your choice. So now you can see that the only solution we need concern ourselves is with D. So we only work out the coordinate of D. So if we were using simultaneous equations, this method would have made our lives so much easier because we would have been able to just work out one set of simultaneous equations to find our points. So here we are, and we know this is our solution, and we can then go and work it out, which we have done over here. We've got D's coordinates down below. Here it is. And so we could answer the question now saying it maximizes at D, coordinate 40, 10, and P would equal 10 times 40 plus 4 times 10, so it will be 400 plus 40, which is 440. So it has a maximum of 440. You can see that this is very streamlined compared to the corner point method. It just saves you a whole lot of work. Of course, it's all about being accurate in how you slide that line. A good technique, if you want to know about, is perhaps this one. I'll just show you back on the graph. What you do is you take your ruler and you square it off against the line, and then you slide. That'll keep your line parallel. So just remember that it's a good technique to use. Right, now I said to you there was even another method. And just so I don't lose these equations because I need them, I'm going to do this method alongside here. And this method is comparing gradients. Okay, so let's get ourselves a color so it's easy to see where I'm working. Okay, I want to just keep those equations handy. So literally what I do is I look at them and I say, what is the gradient of that? Well, if x is equal to 15, it's like this. Its gradient is undefined. So we're dealing with undefined. The gradient of this, well, if it's like this, horizontally, the gradient is 0. Okay, so those are those catered for. This gradient is -1, and this gradient is -0.5. Right, so if we have a look at what we are optimizing, the gradient was -5/2. So now what we're going to do is we're going to look at this and say, between which two gradients does this value lie? Now this particular example is not the kind of example we would use this technique on. So for now I'm going to leave this alone, and when we get to the examples where we do use this, I'm going to explain it even further. But certainly I think I've presented a really fair argument as to why the search line is the better way to go. Now let's talk about what happens next. Now this was a question where they had given me the graph and they were asking me questions. The really intimidating one is the one that happens next. And let's turn to it and we can have a look through it, and you'll see why I say it's intimidating, but I'm going to show you really a nice way to deal with it. Right, here we go. Question 2. You can see it's just words everywhere. It says the owner of a clothing factory intends to manufacture shorts and trousers, a maximum of 60 pairs of shorts and 40 pairs of trousers can be manufactured per day. No more than 70 items can be made per day. It takes 5 hours to manufacture a pair of shorts and 10 hours for a pair of trousers. A total of 500 working hours is available. Write down a set of inequalities to illustrate the restrictions. Draw the necessary graph to enable you to shade the feasible region. And if each pair of shorts yields a profit of 15 Rand each and each pair of trousers 25 Rand, calculate an objective function which will enable you to determine the profit. Determine the maximum profit. Now, my goodness me, how do you even start to deal with something like that? Well, the good news is there is a way that I use that has been always very successful for my students. And so hopefully you will enjoy this and it will make it easier for you to arrange your thinking in this. What I do is I make use of a table. Now, I would start again with a question. First of all, I would read it right the way through, because it's quite important that I understand if there were any problems. So often they'll say in the question, let the shorts be X and the shirts be Y, or whatever. And if you haven't read the whole question through, you can start this off and end up getting yourself into trouble. So I personally would read it right the way through, and then I would go back to the question. Now, they haven't said what X and Y is. So what I'm going to do is I'm going to call my shorts X and my shirts Y. Sorry, I apologize, my trousers Y. I've just decided shorts and shirts instead of shorts and trousers. Right, trousers Y. Here I'm going to make minimums and maximums. Okay, now I need the words to start the table off, so I'm just going to do this. Okay, now, he intends to manufacture the shorts and the trousers, a maximum of 60 pairs of shorts. So we're not talking about our trousers, we're only talking about our shorts. So a maximum of 60 pairs of shorts. So X must be less than or equal to 60. So you see how I organize it? Then they say, and 40 pairs of trousers. So again, I'm just dealing with my trousers. I'm not dealing with the shorts at all. So Y, the maximum must be 40 pairs of trousers. Can be manufactured per day. No more than 70 items can be made per day. Now, items means we're talking about the shorts and the trousers. So what I would do here is I go X plus Y less than equal to 70. All right, so that's involving both of them. Now it says it takes 5 hours to manufacture. So now what I'm going to do over here, I'm going to write hours. Because sometimes they'll give you more than one process. They might talk about machine hours, manufacturing time, all sorts of funny things, and you need to organize. So they can see I had an extra column here. It hasn't really affected these. But here with hours, I'm going to put it there. Now it says it takes 5 hours to manufacture a pair of shorts and 10 hours for a pair of trousers. A total of 500 working hours is available. Total means you can't have more than that, so it's less than equal to, and all I do is I put the X and the Y in here, and there we go. I've now got my set of equations. However, those are my explicit equations. They are coming from the information we are given. Remember last time I mentioned inherent or implicit constraints, and basically those are contained within the situation. Now the situation is he's making shorts and trousers. Can he possibly sell half a pair of shorts or a quarter trousers? No. So we know immediately that the trousers and the shorts have to be whole items. So we are dealing with whole numbers. We can have no shorts, we can have no trousers, but we can't have a negative quantity, so we can't have negative numbers, and we can't have fractional quantities. So what we would do is we would add in here X and Y are elements of whole numbers. Now if you remember your number system, it's naturals with a little naught attached. Okay? Or you could have done the following. You could have said X and Y bigger than or equal to 0, and that may be the way that you've been shown. X and Y elements of naturals. It's really up to you. That is effectively that, because you can't have a whole number that's negative, so it's fine. Right, so now we're ready to draw the necessary graph to enable me to sketch the feasible region. I've done the inequalities. Now I need to actually represent these on a graph. So what I'm going to do is page over. I have already moved the equations to the next page just so we don't have to page between them. So let's go over there and see what we've got. We've got that. Right, now as you can see, we are working with whole numbers, so we certainly don't need to work in the other quadrants. Only the first quadrant's necessary. So what I'm going to do is I'm going to go across here and I'm going to actually put in a nice big fat axis. Of course, it's quite important that you draw your axis that you've got lots of room to maneuver. You don't want to have a little squash graph that you can't read anything on. So that is your first prize. Okay, let's go back here and let's have a look at the graphs. Now, that one looks like 60, 40, 70. Here it looks not so good, but if we look at it, we can divide through by 5. And if we do that, we're going to get x plus 2y less than equal to 100, much better. So 100's not bad. So it looks to me as if I could probably mark up here 40, 50, 60, 70, 80, 90. I probably need a little bit more. Let's just see. No, it's the x I'm going to need the 100 in. 3, 4, 5, 6, 7, 8, 9, 10, 11. Right, there's my x-axis, there's my y-axis. Here's my origin. And now we have to be very thorough about this. This is a graphical representation of a problem. So we need to be very specific. So what did we call our x? Our x we called our shorts. So what I'm going to do is underneath here, I'm going to write shorts. And on the side here, I'm going to put trousers. Okay. Now, remember we talked about how we represent these graphs. This is x smaller than equal to 60. I'm going to call this graph number 1. And if I'm going to draw that one, there's 10, 20, 30, 40, 50, 60s over here. And we know it's just going to be a straight line special case like this. There it is. And where we're going to shade this, well, it says less than equal to, so we want to shade this way. Now notice I'm not getting too carried away with how many arrows I'm putting there. I'm just putting one there because I can see I've got 4 different graphs I have to draw on here. Notice these 2 have been taken care of already because basically I only drew the quadrant that involved them. So for now, I'm going to just take them out of the way so we've got more room to maneuver, but they are catered for already. Right, so what I'm going to do now is I'm going to label on here number 1. So I know that that's graph 1, and so does my examiner. They're not confused about what I'm doing here. Right, the next one says y is less than equal to 40. So let's go over here and let's pick up a line. And 40, there's 10, 20, 30, 40. It's a special case again. Let's put it in like that. And y less than equal to 40, equation number 2. Less than equal to means shade underneath, so I put it there. And at this stage, I can see that it would make sense to put my arrow here down there because it's obviously going to be in this block somewhere. Right, now we get to this one. X plus y less than equal to 70. This is my equation 3. Now, using that technique I showed you just now, if x is 0, stick your finger on the x, and you can see y will be 70. And then if y is 0, put your finger on the y, and x is going to be 70. So we have coordinate 0, 70, and 70, 0. So let's do that. This was 40, 50, 60, 70. There we are. And on the x-axis, it was 60. This is 70. There we are. And now we're going to stretch our line across over that. And as I say, we might have to do some wonderful manipulations if I don't get it right, but it looks like I've hit it lucky this time. Okay, so over here, this would be number 3. And in terms of my drawing, where would I be shading number 3? Well, I can see that if I move that x over, it'll be y less than, so I'm shading underneath. All right, so far everything's pointing to this little portion over here. Right, we've still got this one, x plus 2y less than equal to 100. And this is going to be my equation number 4. So for the purposes of this, I'm going to just take that out so it's out of the way. And this was equation 1. All right, so now doing this last one, we're going to use a similar kind of procedure. If x is 0, so we're blocking it up, we can see the y is going to be 50. And if y is 0, we can see that x is going to be 100. So we can plot 0 against 50 and 80, 90, 100 over here. And we're again going to stretch our line down from there to there. And we're going to label it number 4. And where we're shading, again, we can see it's 2y less than equal to, so we're shading underneath. Right, so our feasible region, and this is where it's not a bad idea to have some highlighters, is this area here. Okay, I won't win any prizes for colouring in, but it's fine, it'll do just fine. Okay, I need to make it clear to my examiner what I'm referring to. And then the thing I would do now is I would label it. So I go A, B, C, D, E, and F. So what I would do to make sure they're not at all confused, I would say A, B, C, D, E, F is the feasible region. And just to make sure that they know I'm only dealing with the natural numbers, I would write this in as well. And just to make sure they really are not confused, I highlight it so they know that that's the area I'm referring to. Okay, right, so we have done that question. Now it's looking very attractive. Just one thing we must mention. Remember the one example I did last time involved a dotted line crossing a solid line, and then we had to worry about whether it was included or not. This one, the good news is everything is solid. So A is included, B is included, C is included, D is included, and E is included, and F is included. So we don't have to worry about that side. Right, let's go back to the question and see what they asked next. Right, next they said, if each pair of shorts yields a profit of 15 Rand. So back to our little table over here, and I think we can just clear this away so we can do the profit underneath. Let's do it in orange. So they're saying a pair of shorts yields a profit of 15 Rand, and a pair of trousers yields a profit of 25 Rand. So that means 15 for every X and 25 for every Y. So that would give me my equation, P equals 15X plus 25Y. Now, that is what they asked in this question. They asked you to find the objective function. In other words, to find the equation that you would use to maximize or minimize your profits. And that comes from what the shorts or trousers are selling at and what sort of profit you're making. So right, now once we've done that, they say determine the maximum profit. Now remember, I've mentioned 3 methods. The first method is the corner point or simplex method, and I've explained to you that when there are lots of points, it can be quite tedious to do. Now there are 6 points that are on the feasible region there alone. That's going to be lots of work. Or the search line, which I say is perhaps your easiest one, because you draw a line, you search, and then you only worry about the point that is going to maximize or minimize. And the third one is the gradient one. This is still not the ideal example to be doing the gradient method on. So let's go to the drawing now and look at it. So it's 15x plus 25y. Profit is 15x plus 25y. Now, what did I say to you we do with this? I said to you the first thing we do is we change it into y form, because the search line is only interested in the gradient of this thing. So first thing I'm going to do is spin it around. So 15x plus 25y equals p. You don't have to do that, but I find if you don't, you're inclined to go wrong. So rather do it. So 25y equals minus 15x plus p. Divide by 25, divide by 25, divide by 25. And so y is equal to minus 3/5 x plus p over 25. The thing I'm interested in is the gradient minus 3/5. So right, let's go over here. We want to plot a gradient of minus 3/5. So if we look over here, here's the 30. So instead of using minus 3, I could use minus 30 over 40, because effectively 30 over 50. Okay, so in that case, 30 over 50, 50 being over here, those are where my search line are going to be. So let's go and get a dotted line, because remember I talked to you about using a dotted line for the search line. That way it distinguishes between what we know and what we don't, we are using to optimize. Right, so now we're here, and you can see there's my search line drawn in, and maybe I need to just doctor it a little bit. I see it's not quite in line with that 50. Yeah, that's pretty much right now. Now remember I said to you, we need to search it, so I'm going to clone it. So I've got another one to search with. Now I lift the one up and I take it on its way, and I want to maximize. So I want the last point of contact. And I can see my last point of contact is going to be at C. You can see once I take it back here, down the bottom, that would be my first point of contact. But as I slide it up, I'd see it hits the corner point A, no good. And it's past E already, it'll hit D, no good. Hit B, which is no good. And the final last one is C, so that's my optimal position. So that's optimal position, and this is my search line. So do you agree with me now? The only thing I'm really interested in is that point C. Now, you can see I've particularly used block graph paper to draw this, so that you can just read off the solution, and in a lot of cases that is exactly what they would expect. And I think it's very clear that C's coordinate would be, let's have a look, that's 10, 20, 30, 40, and that's 30, so it's 40, 30. So this one is easy enough to just do by reading off. There's the optimal position. So it maximizes when there are 40 shorts and 30 trousers, maximizes profits, and the profit is, and what you would do now is you would substitute into this equation. So P is equal to 15 times 40 plus 25 times 30. All right, it won't harm us to do some arithmetic. So that's 600, I hope. And this here is going to be 750. And if we add that up, we're going to get 1350. And so that's our maximum profit. And so we'd write that in rands. Profit is 1,350 rands. And that's how you would end this question off. Put it in a cloud so you can see it there. Really lovely question, and these things are worth so many marks. And I think for a few seconds I'm actually going to stop and show you how they would allocate marks more or less in these kind of questions. So let's go back up to the equations and talk about that. Let's take the orange one. You would get a mark, a mark, a mark, a mark. So you would get 4 marks for having found those equations. You would also get a mark for your inherent ones for saying that, in effect. Then what you would do is you get a mark per graph. So you would get a mark, a mark, a mark, and a mark. And either 1 or 2 for the feasible region. Let's call it 2. So at this stage you can see you're looking at so many marks. That's 2, 4, 6 marks just on the drawing, and I think it's 5 marks on the equations. You've got 11 marks already, and it's a relatively easy thing to do. Then what did they ask? They asked me for this. You'd certainly get a mark for that. And then for actually maximizing, you would get a mark for your search line, a mark for identifying your point, and a mark for giving that. So you're looking at about roughly 16 or so marks, maybe even more, but certainly that many. So this is a really good section to do very well in, and if you can do very well in it, it's like guaranteed marks. The good news is they don't penalize you if you make a mistake. Say, for example, you write down a wrong equation. Now, that doesn't mean you're going to get 0 out of 20 or 0 out of 17. They say, okay, fine, you lose that mark. Now, if you take your incorrect equation, plot it correctly, they will give you that mark. And if you get a correct feasible region for your wrong equation, they will mark that right. And then if you optimize according to your wrong thing, they will also mark that right. So in the end, you might lose maybe 2 marks out of the whole question for one little error maybe writing a wrong number or whatever. So the good news is it's not so traumatic, although it looks horrific in all the words and in the fact that you have to go and do all this work to actually optimize and all this work on this paper. It's actually a lovely section. Let's move to another example. All right, this question involves us being given a table. Now you might notice the previous one, I gave you words and I asked you to organize the table. This one, they are giving you a table and words and you're going to have to sort it out. So let's see what it says. A building corporation decides to develop a new housing area, which is planned to accommodate up to 540 people. Now, up to 540 means its maximum is 540. It proposes to build at most. Now, this is not natural language for us. We don't normally walk around saying at most and at least. We don't do that. But at most means not more than, okay, less than. So it proposes to build at most 120. So there can be up to 120, but no more than that. 121 can't be. Details are as follows. In a 3-apartment, the number of people per house is 4, and the monthly payment is 360 Rand. In a 4-apartment, 6 people will live, and the monthly repayment will be 480 Rand. If the corporation X builds X 3 apartments, so they're telling you call this X, and Y 4 apartments, they're telling you call it Y. So what's happening here is they've sort of spun it, my little table idea, around and have sort of put it the other way around. Now there's nothing stopping you changing that. So if you're finding that stressful, go and renovate. So 3 apartment is X and the 4 apartment is Y, and these are the min and maxes. Now, they're saying to me that there are 4 people in this and there are 6 people in that. And for now, that's good enough. So if I wanted to, I could spin it around. And what did they tell me? They told me it had to accommodate up to 540 people. So 540 would go in there, and we go less than equal to, we tag in an X, we tag in a Y, and we put a plus sign between them. And that is effectively our first inequality. Right, now the next one, well, it goes on now and it says the maximum number of houses and the maximum number of persons to be accommodated. So the maximum number of houses is sorted out. The proposed building here, well, what do we know about that? Well, we know that if we just add X to Y, because that's how many houses we're dealing with, it must be less than equal to 120. So the maximum number of houses, the answer is X plus Y less than equal to 120. And the maximum number of persons is 4X plus 6Y less than equal to 540. Of course, nothing's stopping you simplifying this equation down. In fact, let's do it straight away. Now, if we look here, we can see 2 divides into everything. So we're going to have 2X plus 3Y less than equal to 270. Right, now we have to represent these graphically. Now, of course, we were dealing with apartments. And as you know, that if it's going to be something like that, it's not going to be half an apartment or quarter of an apartment. So we also need to write down there that X and Y are elements of the whole numbers. Now, we're going to represent them graphically. So let's go to the next page where I've got a Cartesian plane waiting. You can see I've marked it already, your X and your Y axis, which you know to do. And over here, I would go 3 apartment. And over here, 4 apartment. Whatever that may mean. Maybe it means bedrooms or something, I don't know. And now I'm ready to actually draw these things. Now, if I look at these, if I look at this first one, if X was 0, Y would be 120, because remember, I block the X up. And then if Y is 0, the X is 120. So we've got that. This one here, if X is 0, Y is going to be 90. And if Y is 0, X is going to be 135. Okay, so that gives me the points we have to plot. Right, so let's go across the graph now, and it looks to me as if we mark up in tens, we'll be fine. I'm just going to put in some. In actual fact, the important ones to put in are the ones that you're going to use to draw. So I'm just going to mark in little markings. Of course, they have to be accurate. The scale must be consistent on the X and the Y axis. so that we are sure that this graph will be easy to read off solutions. Right, so if we look at the first one, it's going to cut at 120, so that's 20, 40, 60, 80, 100, 120. And this one is same thing, so it's 20, 40, 60, 80, 100, 120. And so we would now pick up our line, and from that 120 through to this 120, we would draw our line. Right, now, we are shading y less than, so we are going underneath. Right, let's look at this guy. If it was 0, then it was 90, so if we look, that's 100, there would be 90. And this would be 135, so that's 130, 135 would be about here. And again, we're going to draw this line in from 90 to 135. And our shading for this is also underneath. So at the moment, we're talking about this little portion here, because we do know that x is greater than 0 and y is greater than 0, because after all, we're dealing with whole numbers. Right, so let's highlight our feasible region for the examiner or the person giving me a test, the teacher. And as you can see, we can highlight just the outskirts, but we might as well make it look beautiful. So let's color it in. And there we have our feasible region. Now, after we've done that, we label the feasible region. So I'm going to go A, B, C, and D. And I'm going to write here A, B, C, D is feasible region. And just to make sure no one's confused, x and y are elements of the whole numbers. And even more so, to make no one confused, I'm going to highlight so they're clear that the highlighted area is what I'm referring to when I refer to region A, B, C, D. Right, so now we have to actually go about the rest of the question. So let's see what it said. If we go back here, it says, write a linear equation in the form which expresses the gross monthly rental. Well, they did tell me something about that. Over here, they said the 3 apartment is at $360 a month, and the 4 apartment is at $480 a month. So we can say the rental is 360x plus 480y. And that would be this question answered. No problem with that. Now it says, what number of each type of house should be built to ensure a maximum income? All right, so now we need to go to our graph. So we have rental is 360x plus 480y. And what we need to do now is we need to actually get the gradient in order to draw our search line. So the first thing we're going to do is we're going to spin this around. So 480y plus 360x equals r. So we can say 480y equals minus 360x plus r. And then we're going to divide through by 480 all the way through. So we're going to get y equals this thing, which I could make minus 36 over 48x plus r over 480. And remember, the only thing I'm interested in is the gradient. So I'm just going to work with this part. Now let's make it look more user-friendly. So I'm going to say 6 divides into there 6 times, and 6 divides into there 8 times. So the gradient I'm interested in is minus 6 over 8. Now if I go to this thing and I want to plot that, it would make sense to use 6 little bars. So that would be over here, down 6, and 8 across. So it would bring me here. So in actual fact, I'm using 60 and 80 to get my line. And that's no problem. And here's my search line. And I would have to see if that's, yeah, it's quite all right. It's coming nicely. All right, so now we are ready to go with this. And we now need to search our region. Now I can clone it, so let's clone it, and then we can just use the clone line. And as I go through it, I can see that it's not going to reach a maximum until I get to B. At B, it's in the correct position and all is well. So this was my search line, and this is the optimal position. So all I'm interested in is that point, because that is what the point I'm interested in terms of this drawing. So I need to now go and have a look and see if I can read off this coordinate, because if I can, there's no problem. And I actually think we can. So it's wonderful news. So let's have a look at it and see. Well, if I look over here, B is there. So I can see it there, and I can see it there. So if I go and work that out, this is going to be 90. And this one over here is going to be 30. So B's coordinate is 90, 30. Of course, if we couldn't just read it off like we did there, we would then go and work it out simultaneously, and we would get that solution. So right, we know that B is 90, 30 is where it actually reaches its maximum. So maximum profit, maximum income actually, or rental if you want to call it that, is obtained. And you must give your answer in words, because the question was phrased to you in words. When 3 apartments and 34 apartments are rented. And if we want to know what the maximum will be, or what the income will be, we would go back to this top equation and we would say, right, it's 480 times 30 plus 360 times 90. And we would work that out and we get an answer, and that would be it. Okay, well, let's just do it since we are here. It's 0, 0, 3. That's going to be 4, carry the 2. That's 144 plus 0, 0, 9 sixes of 54, carry the 5. And that's going to be 27 and 5 is 32. And if we add that together, 0, 0, 8, 6, 4. So there's your maximum profit. So really very easy. You could also work that out in your calculator. It would be no problem at all. Okay, so right, let's move on and see what the next question brings. This question actually came out of a past paper, so it's a very good one for us to have a look at and see what it actually involves. It says a factory intends to market a soft drink with a new flavor comprising a mixture of flavors A and B. At least 800 kilograms, but not more than 1,200 kilograms of the two flavors together are needed to prepare a batch of the new soft drink. So far you're saying to yourself, well, why is she doing this one? It's almost identical to the first one she did. And yes, it is, but there's about to be something a little different that we need to mention. The mixture must contain at least 2 kilograms of A to every 1 kilogram of B. Now, this is perhaps the most tricky part of putting together the equations. And I'm going to spend some time when we get to that in a moment. I'm going to go about it just like we normally do, but there's one little exception here. And at least 200 kilograms of B must be used in the batch. Use the graph to find the most economical mixture if A costs 4 Rand per kilo and B 7 Rand per kilo. Right, so they haven't told me what must be X and Y, but we might as well let A be X and Y be B. And we need a table. So I'm not going to actually draw up a glamorous one, just a little sketch is good. Let's just stick a table in here. Okay, we have A, which we're calling X, and B, which we're calling Y. This is quite important because it tells my examiners what I've called what. And here I have my min and my max. All right, so now let's go through it again. It says at least 800 kilos must exist of the mixture A and B. So X plus Y must be more than 800, but not more than 1200. So X plus Y must be less than equal to 1200. Okay, are the two flavors together, so that's why I'm putting the X and Y together. Now, this next one here, the mixture must contain at least 2 kilograms of A to every 1 kilogram of B. This one can't go in the table. It's the only one that I never do in the table. And how I do that is I use ratio or fractions. Now I can hear you cringing as I say that, but it's really not bad. You're going to read the words and you're going to put it into a fraction, which is then going to sort out into an equation very nicely. So let's have a look here. The mixture must contain at least. Now what does at least mean? I tell you, you must study at least 4 hours a day. That means more than 4. So it's a greater than equal to sign. 2 kilograms of A to every 1 kilogram of B. So A over B. At least we have decided it must be this, must be 2 is to 1. So that's what I meant about taking the words and putting them into fractions. Now all I would do is I'd say, well, my A was X and my Y was B, and I want that situation. Now if I cross multiply that, I'm going to get X greater than equal to 2Y, which in turn becomes Y less than equal to a half X. And that's an equation that we need. Now it's not in my table, but it's not the end of the world. And I just do it with a ratio. So I'll go through it again just to make sure you're clear. This is very, very important. So let's take it away completely and start again. In fact, I think I'll take this column away and we'll do it over here. Okay, so let's do it in blue. The mixture must contain at least. So straight away I know that's the sign. Now what are we doing? We're saying 2 kilograms of A to every 1 kilogram of B. So I go A over B must equal, or not equal, greater than equal to 2 over 1. A was X and this was Y, and this is what I've got. Now I cross multiply this, so I'm going to get X greater than equal to 2Y, which if we spin round becomes 2Y less than equal to X. Now I know it's very off-putting when we write Y's on the wrong side, so I'm just making sure it's this side. And this will become a half X. By the way, it's not really the wrong side, but it's just what we're not comfortable with. We're used to having Y on the left side. So there is our equation ready to go. Okay, and then it says there must be at least 200 kilograms of B in the batch. So Y must be more than 200. Okay, now what is this last thing here? This last thing here is the thing we're probably going to maximize or minimize. They want to know the most economical mixture if A costs 4 Rand per kilo and B costs 7 Rand per kilo. So the cost would be 4X plus 7Y. Okay, so that's for later. Certainly we're going to first draw the graph and then we're going to only come to this. So right, let's write the equations down, and I want to be very careful I don't get these equations written down incorrectly, so I'm going to check a few times. It's X plus Y greater than equal to 800. It's X plus Y less than equal to 1200. And let's just go back and check the other one. Y greater than equal to 200. And this one here, Y less than equal to a half X. Oops, wrong way around. Y less than equal to a half X. Okay. And then all we've got left is the thing we're going to optimize, which is 4X plus 7Y. Okay. Right, let's get ourselves a graph going. I'm going to push those up a little bit while I put the graph together. We need an axis, so let's get ourselves an axis going. Okay, it's always good to actually make sure your axis is very spacious. You don't want a little tiny graph that the people are struggling to read, because then what's the point of it? They can't see if you're right or wrong anyhow. So they will just err on the safe side. Right, now it looks to me as if I'm going to go probably up to 1200, so I think I can take 100 each little marking, and that should be fine. So let's do that. So it's 100, 200, 300, 400, 5, 6, 7, 8, 9, 10, 11, 12. There's 400. 800, 1200, etc. This is your x-axis, this is your y-axis. What are we going to do? We're going to go here, mixture B, and over here, mixture A. That's the origin. Okay, now what I haven't put in on my equations here is the fact that we have x and y, but this time, because we're dealing with kilograms, you can have a fractional amount of kilograms. You can have 0.5 of a kilogram. So this time we're not going to say natural numbers, but we are going to talk about x and y being greater than or equal to 0. because after all, we know that it can't be a negative quantity of mixture. So we know that, and this is going to make life a little bit easier for me in terms of the drawing. Right, so let's go for it. Let's call this equation number 1. And to draw that, we know that it's going to have an x of 800 and a y of 800. And our line is going to start there and end there. Okay. Remember what I said to you to help you examiner. You are going to label, oops, I went and put the wrong pen on. You're going to label 1 on there. Where we're shading, it's y greater than, so we're shading above on this one. Right, this next one, our x is going to be 1200 and our y is going to be 1200. You can go and work it out properly like I've shown you. And so 1200 and 1200, and we are going to draw that line in. And our shading for this one will be underneath, and this is number 2. Number 2. And of course we know that this will happen, and we know that in this end here, that will happen, taking care of that. And now we want y greater than or equal to 200. Well, here's 200, so let's pop that line in. There it is. And this is number 3, and it's greater than, so it's going to look like that. And then the last one is this one, and remember, this is the one we can't do with the x and y intercepts. So what we're going to do is we're going to say c is 0, and our gradient is a half. So there's 0, 1 up, 2 across, and we can draw our line using those points to get us going. Now, where are we shading for that? Well, it's y less than, so we're shading underneath. So do you agree with me if I look at it like this? That area here, this little neat block over here, is my feasible region. And so I'm going to highlight it as I normally have done all along. So off we go, we highlight it. Okay, we label it. We write them a note. And notice this time I don't have to say to them naturals, because it's not naturals necessarily. And so that's what I'm actually dealing with. Okay, so now what did they want me to do? They wanted me to find the most economical mixture. So the most economical mixture means I'm now going to return to this thing. Now by now I'm sure you're starting to enjoy the search line method. If you haven't seen it before, if you've seen it before, well, I'm sure you already are enjoying it. And what we're going to do is we're going to get y as the subject. So we have 7y plus 4x equals c. So 7y equals minus 4x plus c, which means y is equal to minus 4/7 x plus c over 7. We're only interested in this. So we go along here. Let's use blue. If I go to blue, I can see that I'm going to start at the 400. I'm going to go down 4, and I'm going to go 7 across. And I'm now going to draw in my search line, which is the dotted line. And there it is. Right, so now we want to have the best cost. So do we want the cost to be the most or the least? Let's just check that that's what the question asked. The most economical mixture. Well, if it's going to be economical, it's going to cost you less, not more. So what we're looking for is the first point of contact with a feasible region. So let's go back there to the graph, bring it down. And if we slide this line, let's clone it first of all. So we can leave our search line in place. Okay, our first point of contact will be at C. So this time, our optimal position is as we go into the feasible region. So can we just read off this coordinate? Yes, we can. It's 600 against 200. If we couldn't, we would have done a simultaneous equation. Now, of course, what is the cost in this case? Well, in this case, the cost would be 4 times 600 plus 7 times 200. Let's get ourselves some space. which is going to be 2400 plus 1400. And if I add that up, I'm going to get 3800. So that's the cost for having produced the mixture. And this minimum cost happens when 600 kilograms of A and 200 kilograms of B are put into my mixture. Okay, so now you can start to see and appreciate that this section has a lot to do with real life. And it was actually quite interesting. Many years ago, I was with a friend of mine who is an accountant, and he was about to start a business. And what he was doing was working out who he should employ, how many machines he should buy, and all this. So I was amazed when he actually, in effect, did this. And I thought to myself, well, here you go. I wish I'd had a camera at that moment in time to actually record him doing this, because I could have come and shown my pupils, here is someone in a real work situation doing this particular question. So very exciting to see it used in real life. Those of you that are thinking of an accounting career, this was what he was, and he was definitely using that. So yes, very nice to see it in action. Right, let's have a look at another question. Now, this is another kind of question. So far, what have we done? We've looked at ones where there are lots of words and we have to organize the words. We've looked at ones where there is a table and we're using a partial table to carry on going. That was our 3-apartment, 4-apartment. We've looked at ones that require me to work with ratios. So now all that's left is what happens if I get a graph and I have to now, remember me talking about this gradient method. Well, this is where this is going to come in a little bit, and I'm going to talk about it in a minute. Let us quickly just have a look at what this question says. Right, if I look at this question 5, they give me this drawing. They say the graph above represents the constraints and the feasible region to a watch manufacturing problem. A watchmaker can produce at most 4 titanium watches a day and at most 5 kinetic watches per day. The maximum number of watches he can produce altogether is 6. Determine the equation of the lines and hence determine all, and now notice they've bolded that. Always ask yourself, why is something bolded? There must be a little trick or a little something that needs to be aware of. Otherwise, why is the teacher or the examiner drawing your attention to it? So the good news is, yes, I probably think there is some kind of trick. So let's start with the first part. Now, the first part we did in our very first question, the last question of last session and the first question here. We are going to find the equations of these lines. Now, in actual fact, we don't need that line. It's not part of the feasible region. This one we do. So what I like to do, and this is something worth remembering, I highlight them as I find them. This one is easy, you agree. It's going to be x is smaller than equal to 5. No problems with that one. This one is also easy. So this one here, we can say that y is greater than equal to 0. We don't really need this one because we're not really using it, but we do need this one and this one. So let's have a look what we know. We know that this one, let's start with this one first, cuts at 6 at the top and 6 at the bottom. Now the way I've shown you is the quick easy way is to say the change in y is 6, the change in x is 6. 6 over 6 gives me a gradient of 1, but this is a negative gradient, so it's negative x. So the equation is y less than equal to negative x plus 6. But I'd like to show you something else that is very, very useful. It used to be a formula we learned in analytical geometry, but it doesn't seem to be featuring in our new syllabus, but it is incredibly useful. If you have the x and y intercepts, there's a formula that looks like this. It goes x over the x-intercept plus y over the y-intercept equals 1. Now all we would do is we would go x, and the x-intercept would be 6, plus y over the y-intercept, which is 6, equals 1, and we times through by 6, and we would get this. Once we were there, we could see that the shading is underneath, so we want smaller than equal to. And that would give you the equation in 2 ticks. But the other way is perfectly acceptable and not a problem. So this is x plus y less than equal to 6. This one, a little bit more exciting. Okay, we can see that this one here has the origin as one of its points. So to do that, let's just take that away. We can use the coordinate 0, 0. But in order to do this, we need to have at least one more point. And I can see from my graph that this point over here will be 2, 4. 2, 4. Now, I can use my gradient method by saying the change in y is 4, the change in x is 2. So 4 over 2 gives me 2. And it'll be a positive gradient, so it's y equals 2x. Or I can use my good old traditional formula for my gradient and work out the gradient normally. So it's 4 minus 0 over 2 minus 0, which is 4 over 2, which gives me 2. So this equation is y less than equal to 2x, because we know it's not going to cut the y-axis anywhere else, but it's 0. All right, so that takes care of those graphs. Very simple, straightforward. We have seen this before. Okay, let's just get ourselves some space again. So I think what I'm going to do is I'm going to jot these equations down here. So we've got them at hand. It's y less than equal to 2x. It is x plus y less than equal to 6. It's x less than equal to 5. And it's y greater than equal to 0. Let's just check. It's 1, 2, 3, 4 lines. That's correct. Now, why is that all there? Why are they stressing that all, if that is all there is to this question? Well, they say to me, the graph above represents the constraints of a feasible region to a watch manufacturing problem. A watchmaker can produce at most 4 titanium watches a day. Is that catered for here? Well, what have we called X and what have we called Y? It's not totally clear here. And at most 5. But we can see from that this here must be the kinetic, and this must be the titanium. Okay, so let's just see, have we catered for that? Yes, there it is. There was a pretty useless inequality, because in actual fact it should have been less than, so you could have added it in. You could have written y less than equal to 4. But in actual fact, it didn't really affect our feasible region in any way. Right, so now we go over here. What else do they say? They say the maximum number of watches he can produce altogether is 6. So do we have an x plus y less than equal to 6? Yes, we do. And so that's catered for. So I think the reason they used that word all is in case you didn't put that one in, which is what I didn't do. And only that all alerted me that I had to go looking again to see why they'd put that word there. All right, so that takes care of the first part of the question. Now it says, if the maximum profit he can make is 500 Rand for every titanium watch and 1,000 Rand for a kinetic watch, write down an objective function. Now what have we done? We've called the kinetic X and the titanium Y. So that means he makes 1,000 on every X and he makes 500 on every Y. And this would be the profit equation. So that's easy enough to write. You can use the table to get it out. Now it says, what is the maximum number of each type of watch he can produce and how much profit can he make? So now what we're going to do is we're going to take this equation we've just done, using the graph they gave us. We're going to maximize on it. So let's take it up again. So it's 1,000x plus 500y. Now remember, the object here is to get y as the subject, so I'm going to be a little naughty and miss a few steps. So it's 500y minus 1,000x plus p. Dividing by the 5, it's minus 2x plus p. So the search line must have gradient minus 2. That's okay. Now, do we have an accurate enough graph to do that? Yes, we actually do. If we look at this graph here, we want a gradient of minus 2. Let's make it blue. We're going to start over here, go down 2 and only 1 across. And now we're going to put in our search line, which is my dotted story. And I think I have to just do a little bit of stretching and pulling to get it in the right position. And there it is in the right position. Okay, let's clone it. And we want the maximum profit, so we want to slide this to the last point of contact, and there's the last point of contact. And yes, I can see that over here, this is our maximum of 5 against 1. Okay, so in actual fact, 5 kinetic and 1 titanium ensures my maximum profit. So let's just go and write that up. So we want 5 kinetic and 1 titanium ensures maximum profit. And to find the profit, we go profit equals 1,000 times 5 plus 500 times 1, which is going to be 5,000 plus 500, which is 5,500. And that would be the end of the question. So the maximum profit of 5,500. Okay, nice question, a little bit different, not hugely problematic. They gave us a really nice graph we could use, so all was good. So right, let's go to the next question. This next question talks about us having a similar situation with a shaded area. And again, they're saying the shaded area shows the feasible region which satisfies a number of constraints. They tell me that P is equal to 2x plus 3y, and they ask me to determine by using the graphs of x and y the values which maximize the value of P. All right, so that is not too bad. If this drawing is accurate, and hopefully it is that, we can actually get away with this quite easily. Because all we're going to do is we're going to go over here, and we're going to get our equation into y form. So 3y is equal to minus 2x plus P. So y is equal to minus 2/3 x plus P over 3. Gradient I'm going to work with is minus 2/3, so it's down 20 across 30. Let's pop in the line. So this is not bad. This is relatively straightforward. Okay, and I think they want me to maximize. Yes, maximum value of P. So what we want to do is search this region with our search line. So let's clone, search line up. You agree with me, it's not the maximum yet. Keep on, wrong one. Okay, up there I can see is my maximum value at M. Okay, and I can see from this value that it's not going to be too problematic because this is going to be the coordinate 10, 70. So it's easy enough to answer this. So we can say this question here, x will be 10, y will be 70 to give maximum value. They didn't ask for the maximum value, but if you went and worked it out, well, that's okay. Now, this very last question is what we use that comparing gradient method for. But before I move off that, I just want to bring your attention to something. If we look at this, what would the gradient of this line have been? It would have been, hopefully you can see, minus 1. This gradient would have been undefined. This gradient here would have been negative 2. And this gradient here would be from 10 to 20, so it's 10 over 61/6. I think, I must just check I'll not tell you a lie. 60 to 20 against 0 to 10. Let's just make sure. So it's going to be 20 minus 10 over 60 minus 0. Yes, I'm right. It's 1/6. Okay, just to make sure we don't want any errors here while we're working. Right, so I just happily jump to the bottom of the page. Let's go to the next question. It says, if the coordinate of point K minimizes the function value of C, where y equals mx plus c, find possible values of m. Now, let's just look at the one we've just done to just get some perspective here. Well, we know that the gradient was minus 2/3. Now, if we look at this, oh, sorry, I just drew that very skew. This gradient was minus 2/3. And do you agree with me that if we're going to look at it, if I'm going to start moving around this gradient, things would change? So I think let's just go straight to the question because I'm a little bit worried about time and finishing up what we need to finish up. So let's go here. I'm looking for this. they tell me that it minimizes at k. So that's the solution I want. Now, in actual fact, what I do with this gradient method is I know that this thing will optimize, or will be achieved at this point. Okay, so now this point can obviously take various angles. So let's just quickly take this out, put in a line I can wiggle around, because that's quite important. Let's put it in here. I just want to take this one out so we don't get confused. Cut. And I want to take this one out, and we can just work with this. Now, what am I doing? I want to know what the possible values are for this. Now, do you agree with me that if I wanted to, I could have made this search line much more steep, and it still would minimize at k, or I could have made it more shallow, and it would have minimized at k. But you agree with me that eventually, if I keep on making it shallower and shallower, it will superimpose on this line. Now that raises an interesting question, because if that does happen, that means that any solution along that line will be true. So you would have to give me all answers on that line. So we don't want that. So we want it that its gradient is going to lie between this one's gradient and that one's gradient. So it's not too hard to do. All we're going to do is we're going to say, right, our gradient has to lie between 1/6 and -2. Oh, do you see what I just did there? Silly me. Obviously, the smaller number happens first, and the bigger number this side. So I know that my m value has to lie from -2 to 1/6. So if the gradient had been -1, it would have minimized there. Okay, obviously it wouldn't have maximized there, it would have minimized, it would have been the first point of contact. Now, it also enables me, but they didn't ask this in this question, and they seldom do, to talk about what C could be. Because obviously if this line is going to lie between here and here, the C value has to lie between 10 and 60, because that's where those two lines are. So if I had asked you, you could have answered me between 10 and 60. But they didn't ask you that, they only asked you that. So in actual fact, if I asked you, it maximizes over there at L, you would have answered me in the following way. You would have said, well, the M lies between, and it's 1/6, and that is -1, so it's -1 and 1/6. And that would be maximizing. And yeah, it's just interesting to know that there are all these many methods. And I hope you enjoyed getting all your linear programming under control. It was really good being with you, and I look forward to being with you soon again. Bye-bye.